Assalamu alaikum, everyone. Welcome to Mathematics with Shahab Yaqub. So now let's start the concept of central limit theorem. It is part and parcel of sampling and estimation, and it will be used in the concept of hypothesis test also. So now what exactly is central limit theorem? We call it CLT in short. What it says is this: any non-normal distribution will start acting normally provided the sample size is large. Now, what is the definition of large? The definition of large is if n is greater than or equal to 30. If the sample size is greater than or equal to 30, at least 30, then CLT applies. And it will become a normal distribution scenario, and you will apply all the principles related to normal distribution. Now, for example, there are 6 cases in which I have divided this thing. Case 1, in which mean and variance is given. So let's say the mean is given, let's say the variance is given, and the sample size is 30. So even though it's not specifically stated that it follows the normal distribution, we will say now, since n is greater than or equal to 30, CLT applies, and we can just make it a scenario of sampling distribution. X bar follows the normal distribution. The mean will come over here. The variance will come over here, divided by n, where n is the value of the sample, the number of sample. And then you can just work it out. Whether you are using the 7 rules to calculate probability, or whether you are using 2 rules to use probability to find X bar or something else. So in 7 rules, we find probability. In 2 rules, probability is given. And then they can ask for either n, like you have just seen in one of the questions, or something else. Now, this question, we did it in class yesterday. Let me go over it. The question says, over a long period of time, it is found that the amount of sunshine on a day in a particular town in Spain has a mean 6.7 and standard deviation 3.1. Now, in the first paragraph, it does not state that it follows the normal distribution. So, first of all, it's asking, find the probability that the mean amount of sunshine over a random sample of 300 days is between such and such. The second part, give a reason why it is not necessary to assume that the daily amount of sunshine is normally distributed in order to carry out the calculation in part 1. That means the examiner is aware of the fact that some people would just not read it carefully and they would just start off the question. Let me assume that I start off the question, I write X bar follows a normal distribution 6.7, 3.1 square divided by the number of sample, which is 300. And this assumption is working out. Why is this assumption working out? This assumption is working out because the number of sample is large. So we would say since n is greater than or equal to 30, CLT applies. And then whatever we are doing, that is perfectly all good, all clear. The rest of the working, I'll simply write it down. Probability X bar lies between 6.5 and 6.8. Probability Z lies between 6.8 minus 6.7 divided by 3.1 square over 300 square root. And this is 6.5 minus 6.7. And this is 3.1 square over 300 square root. Now we can see that the numerator is positive. We can see the numerator is negative. That means what we need to do is that apply rule number 7, which says if probability Z lies between 2 values, negative B and positive A, we read the table for B, we read the table for A, we calculate the probabilities, we add up the probabilities, not the Z value, and then subtract 1. So that is the rule that is applied over here. Second part, What is the justification? This thing is the justification. Whether the examiner asks for it or not, we should state it. Give a reason why it's not necessary to assume, because sample size is large. It's for 1 mark. So this statement is more than enough because sample size is large, and it's better to say that CLT applies and the examiner knows what CLT is. All good, all clear? Now let's look at this question. Another question. These are all from your topical past paper book. So now the question says a random variable x has a mean mu and variance sigma square. The mean of a random sample of n values of x is denoted by x bar. Give expression of expectation of x bar and variance of x bar. It's just making sure that you understand the concept in and out. So basically for part 1, I'll write x bar follows a normal distribution mu comma sigma square over n. And then we should write it separately because they're asking us. So therefore, expectation of x bar is whatever is written in the bracket, that is mu. And variance of x bar, that is sigma square over n. That is all what you have to write for 2 marks. Now the second part. Now the question says the heights in centimeters of adult males in a town is normally distributed with mean 177.8 and standard deviation 6.1. Find the probability. The mean height of a random sample of 12 adult males from this particular town is less than 176. It's already normal distribution. So therefore, CLT doesn't have to be used. Therefore, the sample size does not matter. So keep these 2 things in mind. Already normally distributed, CLT not applicable. And since CLT is not applicable, it's all about the sample size. Therefore, sample size does not make a difference. So over here, you see that the sample size is 12. So what difference does it make? It's already normal. Even if the sample size is 2, it would work. Even if the sample size is 1, it would work. So therefore, just writing it down for the second part, we will say x bar follows a normal distribution 177.8, 6.1 square divided by 12. And we are looking for the probability. Probability x bar is lesser than 176. Just writing down the steps. Probability z is lesser than 176 minus 177.8 divided by 6.1 square over 12 square root. And then knowledge of S1 is assumed. Now let's read the third part. State with a reason. That means there are 2 things. State yes, no. With a reason. The reasoning should be there, crisp. Whether it was necessary to use central limit theorem in calculation, the first of all, we would say the answer is no. It's not necessary, right, in complete English. It's not necessary to use CLT because the distribution is already normal. The distribution is already normally distributed. It's already following normal distribution. So why should we use the central limit theorem? Why should we make that assumption? Clear? Okay, now another question. Something about back solving. It says a population has a mean. Let me highlight it. A population has a mean 12, standard deviation 2.5, a large random sample. Now, it does not say it follows a normal distribution. It says a large random sample of size n is chosen from this population, and the sample mean is denoted by x bar. Given that probability of x bar lesser than 12.2 is 0.975, correct to 3SF, find the value of n. So this is just like a back solving question that you just did. So first of all, justify. What would you justify? Since sample is large. Since the value of n is not given, you cannot say n is greater than or equal to 30. Just simply say sample is large. So therefore, CLT applies. So therefore, x bar follows normal distribution 12, 20, 2.5. 2.5 square, that's the SD divided by n. Probability x bar lesser than 12.2 is 0.975. Remember, for 97.5%, the corresponding z value is 1.96. So now just do this thing. Probability Z is lesser than 12.2 minus 12 divided by 2.5 square over n square root is equals to 0.975. Probability Z lesser than a positive value. This is 1.96 is 0.975. Therefore, 0.2 divided by 2.5 over root n is equals to 1.96. Hence, you make in the subject. All good? Have another look. Write down the mean and variance of the distribution of sample size n. This is exactly like what we did before. X bar follows the normal distribution, mu comma sigma square over n. Write it separately. Expectation of X bar is mu. Variance of X bar is sigma square over n. Now, let's focus on this part. What, if anything, can you say about the distribution of sample mean if n is large? If n is large, CLT applies. If it's a non-normal distribution, and if it's a normal distribution, sample size doesn't make a difference. And if it's a normal distribution, sample size is irrelevant. Do you get the idea? They are asking this question, what if n is large? If n is large, it depends on the scenario. If it's a normal distribution, it doesn't make a difference. If it's non-normal, then it will become CLT. CLT would apply and it would become normal. What about if n is small? If n is small, if it's normal, then no issue. It will remain normal. And if it's non-normal, CLT won't be applicable. Is this thing all good, all clear? So basically, if it's a non-normal distribution, if the sample size is large, only then it will become normal. If the sample size is small, it won't become normal. Normal distribution, sample size doesn't matter, whether large or small. Now, another thing, this we have not yet studied. This would be the last topic after mocks that we will study. So a question of CRV, a question like this, that can also be related to sampling, but we cannot do it right now because we have not studied. Case number 3, DRV from S1. Now, we know that in S1, we have studied probability distribution, discrete random variable. Values of X are given, corresponding probabilities are given. I've just made up a table. All the probabilities add up to 1. Expectation of X, sigma Px. I have calculated expectation. I have calculated expectation of X square according to the formula. I have calculated variance of X. Now, an exam type question could be like this. A sample of size 50 is taken. From this distribution, find the probability the sample mean exceeds 1.2. Now, we are just interested in mean, which is right over here. So we are interested in this mean. We are interested in this. So this comes out to be 1.8. So these are the two things that we are interested in. It doesn't make a difference where the mean and variance is coming from. As long as we have the mean and variance and the sample size, CLT will apply. So first of all, we will write that X bar follows a normal distribution 1.0, comma 1.8. This is the variance divided by 50. And then they're asking probability X bar is greater than 1.2. Probability Z is greater than 1.2 minus 1.0 divided by 1.8 over 50 square root. And then knowledge of S1 is assumed. That is how this working will be done. All good, all clear? Let me just pause the recording over here, and then we'll continue in a short while. Now, people, there is a small correction that needs to be done. So someone pointed out that when we calculate expectation of X square, that is X square into P, 0 square into 0.4, 1 square into 0.3, 2 square into 0.2, 3 square into 0.1. So by mistake, this is 0.4 over here. This is actually 0.2. So because of this, this 1.6 becomes 0.8. And this 2.8 is actually 2.0. So over here, expectation of x square is 2.0 minus 1.0 square. 2.0 minus 1.0 square, that is 1.0. And let me also write it properly over here. We haven't done the calculation, but things need to be said clearly. So this is 1.0, this is 1.0, and then knowledge of S1 is assumed. Another scenario, that is about frequency distribution. Let's say this data is given, that is about X and F, and we need to calculate the mean and variance. So our objective is to calculate mean and variance by any which way. So now over here, the knowledge that you have used in S1 will be used. So we have X, we have F, all these things are there. And we make a column for X square. We make a column for Fx, that is F into X. And then we make a column for F into X square. So we have sigma F, we have sigma Fx, we have sigma Fx square. We have these formulas from S1 for frequency distribution. That is X bar is sigma Fx over sigma F. And variance, that is SDX square, that is sigma Fx square over sigma F minus X bar square. Now in this question, if it says a sample of size 70 is taken, we have the mean, we have the variance, we divide by 70, and then it's the same working as before. So nothing special. Frequency distribution or probability distribution, it's the same scenario. Now let's look at this question. There are two parts to this question. Try both of them out. And let me also write one thing over here, which we have studied earlier, that unbiased estimate of population mean is the same thing as sample mean. Unbiased estimate of population variance, it's n over n minus 1 sample variance. So why don't you go ahead and try it out for 5 minutes? Let me pause the recording. So now let's look at this question. First of all, the first part, it's about reasoning. The question says, give a reason why sampling would be required in order to reach a conclusion about. The first part, the mean height of adult males in England. We would say that it's not possible to measure the height of every single person. It will be too costly, too time consuming. That's why a sample is required. Second one, the mean weight that can be supported by a single cable of a certain type without the cable breaking. So basically, we are calculating the breaking strength. If we use all the cables, there won't be any cable left for us to sell. That's the thing. Now, the next part, the weights in kilogram of sacks of potatoes are represented by the random variable X with mean mu, standard deviation sigma. The weights of a random sample of 500 sacks of potatoes are found and the results are summarized below. So this is the result that is summarized over here. Calculate unbiased estimate of mean and variance. The very first part, B part 1, X bar, that is sigma X over N, which is 9850 divided by 500, whatever the answer comes out to be. Now, the variance square, the sample variance, that is sigma X square over N minus X bar square. That is 194125 divided by 500 minus X bar, which is 9850 over 500 square. And this is the next thing. Now we are looking for unbiased estimate of mean and variance. Unbiased estimate of mean is the same thing as sample mean. Unbiased estimate of population variance is the same thing as n over n minus 1 sample variance. There is also a direct formula, but I prefer to use this formula because you have already used it in S1. So n is what? 500. This is 499 into whatever the answer for this part was. Second part, that is sampling. So it's a combination of estimation and sampling. The second part says a further random sample of 600 sacks of potatoes is taken. And then it says, using your values from part B, part 1. B part 1, find the probability that the mean weight of the sample exceeds 19.73 kg. That means the special thing about this thing is when we will write X bar follows a normal distribution. So we are using the unbiased estimate of sample mean, population mean, and unbiased estimate of population variance divided by 60, and then you would carry out this calculation. So let me just go to the PDF and let's look at question 16, what they have done. And let me pick up the things from here. So this is question 16, the mark scheme. And let me paste it on this page. Okay. Now this thing over here, 19.7, that is the answer for the mean, the unbiased estimate and the sample mean. And this thing is coming out to be 0.16032. So this is 19.7. And this is 0.16032. That is the sample variance. So now over here, we will write X bar follows the normal distribution, 19.7 divided by 0.16032 divided by 60. That is the data that is obtained from part 1. And then they are asking us to calculate exceeds 19.73. Probability X bar greater than 19.73. Probability Z is greater than 19.73 minus 19.7 divided by 0.16032 over 60 square root. And this value over here, this thing comes out to be 0.580. Probability, this is 1 minus probability Z is lesser than 0.580. The corresponding probability is 0.7191. Final answer is 0.281. So the final answer is 0.281. That is the probability. All got all clear? The third part. Now it says explain whether it was necessary to use central limit theorem. Does it say that it follows a normal distribution? No, it did not. So yes, it's necessary. It's very, very necessary to use central limit theorem. Why? Because the distribution was not normally distributed. But since the sample size is large, therefore CLT is applicable. Now this thing is done. Now the last two cases. Case number 5. This is about binomial distribution. Yes, we can have a question of binomial distribution, and CLT can be applicable over here provided sample size is large. Now keep in mind, when we talk about binomial distribution, X follows a binomial distribution N comma P. Expectation of X is NP. Variance of X is NPQ. And over here, also keep in mind, this N is the number of trials. This has nothing to do with this N, which is the number of samples. These are two different things. Do not mix up the two. So now what we will do is that we will take the NP from here. We will take the NPQ from here. And if N is greater than or equal to 30, then we will say CLT applies. And we will write X bar follows a normal distribution NP comma NPQ divided by this N, which is the number of sample. So do not mix up the two. Now, what kind of question will come? Let's have a look. A past paper question. It says random. Let me first highlight it. Let me just erase this thing. Now it says random sample of size 120 are taken from this distribution. Now understand the difference between the two. This 120 over here, that is the sample size. This N over here, 15 and 0.4, that is for the binomial distribution. That is the number of trial and probability of success. Okay. So now, first of all, write down binomial. Write down N is 15. P is 0.4, Q is 0.6. Let's evaluate NP, which is 15 into 0.4. 4 into 15 is 6. So this comes out to be 6. Let's evaluate NPQ. So this is N, this is P, this is Q. That is 15 into 0.4 into 0.6. 6 into 0.6, that is 3.6. Now we will simply write x bar follows a normal distribution 6, 3.6 divided by this n. This is the number of sample divided by 120. So this is divided by 120. Now, no one has asked this question. What about continuity correction? What about NP greater than 5? What about NQ greater than 5? What happened to this? Nothing happened to this because this is not applicable because CLT is already an approximation. So CLT is already an approximation, so you don't need any further approximation. So that knowledge of continuity correction, that knowledge of NP greater than 5, that knowledge of NQ greater than 5 is not applicable in sampling question. That is applicable in a simple question of normal approximation to binomial or normal approximation to Poisson. It's not applicable over here. So that is why once you get this data, you are back to square one. Describe fully the distribution of the sample mean. So expectation of x bar, that is 6. Variance of x bar, that is 3.6 divided by 120. And what are they asking? Find the probability that the mean of a random sample of size 120, they are further emphasizing that's the sample size, is greater than 6.1. So now you would say probability x bar is greater than 6.1, probability z is greater than 6.1 minus 6 divided by 3.6 over 120 square root, and then you get this answer. All good, all clear? Case 6, what do you think is case 6? Poisson distribution. Case 5 was binomial. Case 6 is Poisson distribution. We know that x follows a Poisson distribution with lambda. We know that expectation of x is lambda, so is the variance of x. Again, CLT would be applicable provided sample size is large and is greater than or equal to 30. So now we would be having x bar follows a normal distribution lambda, comma, lambda over n, where n has to be at least 30. Let's look at this question. The first part, it says x and y are independent, this thing, random variables, each having a Poisson distribution. X has a mean 2.5, y has a mean 3.1. Find the probability x plus y is greater than 3. What is the first part about? X plus y, total. What is it about? Linear combination. Simply add the means. So the first part is about linear combination. So this first part, LC, x follows a Poisson distribution with 2.5, y follows a Poisson distribution with 3.1, x plus y still follows the Poisson distribution with 5.6, and it says probability x plus y is what? Greater than 3. Greater than 3 means greater than or equal to 4, which is 1 minus probability x is less than or equal to 3, which is 1 minus, so this is 1 minus e raised to power of negative 5.6, 1 plus lambda square over 2 factorial plus lambda cube over 3 factorial. So this is linear combination question of Poisson variable. What about the second part? The second part is what? Let's see. A random sample of 80 values of x is taken. Find the probability sample mean is lesser than 2.4. What is this about? Sampling. The second part is about sampling. So this is sampling and of course CLT. So CLT is sampling. CLT cannot be anything else. So now we would say since sample size is large, therefore CLT applies. So now, first of all, it's only about one variable, which is x. What is the mean of x? 2.5. So we will say x follows a Poisson distribution with 2.5. Therefore, expectation of x is equals to 2.5. So is the variance of x. So therefore, what exactly are we doing? The thing is, we would say x bar follows a normal distribution 2.5, 2.5. What should we divide it with? We should divide it with 80. Got the idea? And then it says sample mean is lesser than 2.4, probability X bar is lesser than 2.4, probability Z is lesser than 2.4 minus 2.5 divided by 2.5 over 80 square root, and then knowledge of S1 is assumed. Again, over here, the normal things, normal approx to Poisson, that is not applicable. CC is not applicable. Lambda greater than 15 is not applicable. All these things are not applicable. Why? Because CLT is already an approximation. You cannot do double approximation. So these are all the 6 cases of CLT, and that finishes the lecture related to CLT. Take care, everyone.